Okay, then I can start there. Let's go to the slides here. And just a few words about myself. I'm Franck Pachot. I'm consultant. I've been working 1 year at CERN, but I'm back at DBI Services to do consulting because finally that's what I like to do. I have a few certifications on Oracle and now also on AWS. I work at DBI Services in Switzerland, but we also work remotely. We do consulting, trainings, anything, and everything works remotely, so that's perfect. And now let's go to the topic. So, introduction about the wait events and history about them. So that's a feature that is there for a long time in Oracle. The story of it is related in the Oak Table book, Oracle Insight Tales of Oak Tables. And basically, they explain that at that time, so 1992, they had a problem, performance issue, but the processes were not running on the CPU. And probably on those systems, it was not Linux for sure, but I don't know which system it was. They probably had no tool to trace what happens on the system when it's not running on the CPU. And then they decided to put some instrumentation code in their code. Just to know what the processes are waiting for if they are waiting for something. And this is very old and we still use it today because code instrumentation is always helpful to do some performance or any troubleshooting or understand what happens. For example, the first reason is really see where the time is spent when the database is busy. Because if you don't know where the time is spent, you will do some tuning just with guesses. But for example, if you are sure that you are waiting on a latch, a lock in memory, you don't need to increase the memory. It can only be worse. If you don't know that you are waiting on a latch, you may guess and maybe try some things. Of course, you use wait events also to check resource utilization. You want to see if you are spending a lot of time on I/O besides CPU, for example, or network because you have DB links. In the presentation, we will go through not all the wait events, but the major wait events that are useful to know. And it's also a good idea to look at wait events to get an idea about what the application is doing on the database, like a load profile. Are you running an application with a lot of full scans for reporting, or is it more a short access to few rows, but locking each other? So you see that with wait events. And finally, because everybody is talking about scaling, you can see what scales or not, because when you know the resource you are waiting for, you know if it's something that you can scale. For example, if you run on CPU, you know that you can add CPU. Of course, it has a cost, but you can. If you wait on I/O, you probably can add more disks. If you wait on a lock, for example, you cannot add anything, you will not scale. So that's also very important to see which waits are scalable because the resources can be increased or not. So many reasons to look at wait events. And where is it instrumented? So in the Oracle code. And basically they instrument all system calls. When Oracle has something to do on CPU, there are a lot of statistics to know what it's doing on CPU. But each time it has nothing to do in CPU because it has to call something, I/O, network, memory, memory latch, then Oracle will instrument it, which just means write the timestamp before, write the timestamp after, and then you know the time you waited for it. And what is really good with wait events, it is instrumented in a code, but we have many places where we can see those statistics. We will see a few examples, but you can see them in SQL Trace, in VDollar views, in StatsPack, AWR, if you have a diagnostic pack. And what's interesting with that is that you always work with the same metric, whatever the tool you are using. And then when you see something either graphically or with a command line tool, you are always talking about the same metrics, and most of them documented. Not most of them, but most of the relevant ones are documented. Do not hesitate to interrupt me if you have questions at any time. We will do some homework at the end also if you want to interact and check by yourself. I will share my, my database so that you can see some wait events on it. But do not hesitate to interrupt me if there is any question. When I say that it is instrumented for each system call, I will explain that with a sequence diagram. So this is an example where the client, SQL Plus or the application or anything, is just going to fetch the next rows, for example, from a cursor. So the client is doing a fetch call and expects a result from it. And between the call and the result, the database has something to do. Look at the rows, find the blocks, send them. So in front of your session, you have a server process that is working for your session. This process receives the fetch call, has probably something to do in CPU, and then probably something else to ask to the system. That's the system call. In this example, read some blocks from disk and then ask to the OS for those blocks, get them, work on it with the rows that are in there, and call the OS, and at the end, there is the result. So that's the basic sequence diagram showing two layers. Your foreground process here, doing something in CPU and waiting. During that time, it is waiting. The storage is working, OS or storage in behind. So the idea of wait events is that what happens between CPU work, the server process doesn't really know because it's just waiting. So the idea was to instrument those ones, the blue ones there. And then at the end, you can do some profiling, know exactly the profile of the work you had to do to answer the fetch call. So I've put there the example, working in CPU, waiting for I/O, working CPU, waiting for I/O. Before the call, the server process was just idle, waiting for the next thing to do, for the client asking for something. And then it is working, sends the result, and then again idle. And idle is also a system call. It's a read from the network, from the TCP/IP socket connected to the client. So basically, we can see that the server process, the foreground process, is either working on CPU, doing useful work, or just waiting. And the most important thing there is that all this time that I have profiled is directly related to the user response time. What the user sees is that he waits from the fetch to the result. And what you want to do most of the time when you do some database tuning is just reducing the response time. And if you want to reduce that time, you must know where you can reduce it, where you are working. So the idea of wait events is exactly to do some profiling of this response time. And then if I see that I'm spending most of my time in waiting for IO calls, then I know I will have to look at that, either do less physical reads or faster physical reads, but I will not guess and try to see buffer cache hit ratios or anything. I really can focus where the user response time is spent. So I will not go too deep in the detail. I'm just showing here some disassembly of the code because we are at POUG and we need some hexadecimal and low-level things. But the goal is not to explain the low-level. We will go to the wait events and the wait classes, but this is just to explain you where it is instrumented. Anybody with one line can disassemble the Oracle code. And here I have taken a function. I know that this function is what is doing some IO calls. And when I disassemble it, I see some calls. And the one I'm interested in are this one, the kernel service function that is actually doing the system call. And those ones around are those that are instrumenting the wait events. This means kernel service layer, wait, begin, context, wait, and context. So basically, when Oracle has to do some IO call, just a few instructions before, it checks for the timestamp. At the end, it checks for the timestamp. And then we know the time and the number of calls we have done. So that's the way it is instrumented. Most of the calls are instrumented in current versions. Okay, now we get back to a higher level, and the first view that you can have on wait events is, for example, if you have diagnostic pack, when you go to Enterprise Manager, you see this top activity graphics, and you see them with colors. So those are screenshots from people who have put some art on it. But what's interesting in those are the colors. In green, you will see the CPU, working in CPU. In blue, you will see the IO calls. And you have other colors for the different kinds of wait events, different classes of wait events. For example, the reds are waiting for application logs. The big orange one is waiting at commit from the log writer. We will go to look at the most interesting wait classes and wait events. So in Enterprise Manager, you see them there in those graphics, and you see them also in the load map where you can see all your databases. So here I see, if I know the color, I see that I have in the total of my databases 270 active sessions, and most of them are running on CPU, a few of them are running on IO, and well, that's all. Those colors are quite important because most of the tools are using the same colors, and then it's easy to recognize them. And also they have been chosen on purpose for their meaning. CPU is always there because a database is a software, and software runs on CPU. So this is why it's green. It will always appear. Sorry. Blue will be there most of the time because you are running a database which stores its data on disk. And then you should have to read the disk at some times. The red ones are those which needs your attention, logs, things that are blocked. And there are a few others. We will see all that, and we will look at them also live in a database. Okay, then I will start with CPU time, which is not a wait event. So the topic is more about the DB time. And I will explain that the DB time, which is the response time for the user view, is either working on CPU or waiting on wait events, as I've displayed in the sequence diagram. So let's start with CPU. If you see some CPU usage, what does it mean? What can you do? Is it good? Is it bad? So This is an example where I see that I have 40 sessions on average running on CPU. And I had a peak during 3 hours with up to more than 100 sessions on CPU. I have a few more wait events, but the major ones are on CPU. So it's not a wait event. It's really the database being busy. And then the total here, it's the average number of sessions that are active in the database using some database time. And then before going back to CPU time, I will explain this database time. So the database time is the time spent in the user process where the user is waiting for it. So for the user, it is the response time. For your system, it's the busy time. For the database, it is the busy time. And so busy, CPU, or wait event. And this is when the session is active. Of course, if the server is just waiting to have something to do, we do not count that as a DB time. And basically, you see that when you query $$ session, you see if the session is active. If the session is active, you are in DB time. Then, of course, each session uses some DB time. If you have multiple sessions, then the DB time will be higher than the elapsed time. And there are two metrics for it. The first one is in seconds, the total time spent in database. So if I have 4 sessions that spend half of that time waiting for the database, so 4 sessions, half of that time, I will have 2 sessions active in average. So either you see the metric with the number of seconds using being busy, being active in the session, or you see them divided with the elapsed time, which means that you have an average number of sessions. But you will see that in the next session, probably with some AWR reports. For the moment, I will explain. So what I said, this DB time is the sum of CPU time and wait time. And I'm displaying there the oldest tool that can show wait events, TKProf. We will do it later as a demo, but this is an example of TKProf report, just to explain this maths between DB time, CPU time, and wait time. Here, I have a TKProf of 1 session. So the DB time is the elapsed time during the calls. And I have the elapsed time here of 109 seconds during executions. And I can see that during this time, 109 seconds, I spent 42 seconds in CPU. You remember the sequence diagram? You spend some time in CPU, and in between, you have some system calls. And those system calls are the wait events, and they are displayed here at the end. SQLnet message from client and to client, those are the idle ones where my session was waiting to have something to do. But the interesting one here is PL/SQL log timer. That's a wait event. Actually, it's the wait event that is behind the DBMS session sleep, where you put some seconds. And here I see that I've waited 1 time for a total time, so for 66 seconds. And if you subtract the CPU time from the elapsed time, you should find them in the non-idle wait events. This 109 elapsed time was spent 42 seconds in CPU and 66 seconds in, 66 seconds there waiting. So that's the first thing and the most important thing to know. In TKProf, they are separated. You see wait events on one side and CPU time on the other side. In modern tools, like we have seen the top activity graphs, we just have them added to see the DB time. Okay, back to my CPU time. So CPU is expected. You run in a database and you expect it to do something in CPU, to find a lot of data in memory because you allocate a large cache so that it doesn't have to go to the disk a lot. So of course you expect it to run in CPU, but of course you don't want to spend more in CPU than what you need. And in this example, I can see that most of the time my system needs 40 sessions active in CPU. So 40 cores or maybe 40 threads. But for this peak, I need a higher capacity. My server needs at least 300 cores to be sure that I can handle those peaks. And the problem with that is the price of the licenses, because Oracle license the software counting the CPU. So if you are in Enterprise Edition, you count the cores. If you are in Standard Edition, you count the sockets, but you have also some limits. So here I have to pay for 240 processors or cores. But if I can reduce that, if I find a query that I can tune and reduce that, then the needed capacity may be lower. And then I can put more databases in the same server, and then it will be cheaper. So that's why it's important. CPU can scale. You can use more CPU. You can have bigger servers, but the price scales as well. So you don't want to use too much there. Then what can you do? So CPU time is used mainly to parse queries. When you run a SQL statement, it has to be compiled because it's just text at the beginning. It has to be compiled, optimized, find the execution plan, as you have seen just before with Jonathan Lewis. So this parsing activity has a lot to do on CPU. Or most of the time, because you should not parse always, most of the time the CPU is spent reading blocks. So getting blocks from memory and reading rows within the blocks, all reading rows activity. And also if you have big sorts, if you have some reports doing some sorts, or if you have hash joins, then that requires also CPU. Those are the main three activity that needs a lot of CPU. So then what can you do? And I'm just giving some ideas. The wait events will not tell you what you have to do. The wait events will first tell you where you have to look at, which query, which activity in which query. And then you have to find the right answer, look at the execution plan or anything. But the idea, if you are passing queries too much, use bind variables. If you are on OLTP, where you are running a lot of short queries, they should use bind variables so that they are parsed once and reused. And then you do not consume CPU to recompile each time you execute them. If you read too many blocks, what is too many? For example, if I see a query that returns 3 rows, but had to read 1 million block, then probably there is something to do. And something to do is look at the execution plan and maybe use more indexes or better indexes to have better selectivity for the predicates and read less blocks and then use less CPU. And if you are sorting too much or hashing too much, then sorry, I'm still in the reading blocks also. A reason for a lot of CPU usage may be doing nested loops. That is optimal for few rows, and doing a lot of loops and then reading always the same blocks. And then in those cases, using hash join when you have many rows is better. So Using hash join means you look at the execution plan and you try to understand why it's not using hash join, maybe look at the statistics or the solution is not there. But if you see that you use a lot of CPU reading blocks, then look at the execution plan for those queries. And sorting, one thing we see quite often is select star or select all the columns, because that is generated by default from Hibernate or something like that. If you select a lot of columns and sort them, Oracle has to sort all that. But if finally you need only 2 columns, better to select only those 2 columns, and the amount to sort is shorter. Okay, that was about CPU, and now we will really look at the wait events. When we are not in CPU, we wait. And the most important waits are IOs. But before going there, we will not look, when I explained that the DB time, the response time is the sum of CPU and wait events, be careful, do not look at all wait events, only the foreground ones. And what I mean by that, I take an example again with a sequence diagram. When you commit, you have a transaction, you did some work, and you commit, the client says, please commit. Your foreground process actually will tell the log writer, please ensure that all the redo is on disk, because I cannot tell my user that the transaction is committed if I'm not sure that all changes are persistent on durable storage. So when I commit, most of the time in my foreground session is on log file sync, waiting for the log writer. And that's a wait event. But then the log writer has something to do. It reads the buffer, the log buffer, so that's in CPU, but it also has to write to the redo log, the redo that covers my transaction, and waits that it is written, and then go back and tell my foreground process, okay, that's done. And then my foreground process can tell the client, yeah, it's done, it's committed. Here you see 2 wait events. But if you want to compare the wait events with the response time, you cannot add them because they happen at the same time. You have to either to count what happens there or what happens in your foreground process. And this is where you will count the wait events in your foreground process. We say that the other ones are idle just because you need to count only one. So here, my DB time will be the CPU time in my foreground process and the wait event in my foreground process, which is log file sync. That doesn't mean that I do not have to look at the log file parallel write. If I see that I'm spending a lot of time there, maybe I will check that. But in a graph that shows the average active sessions or the DB time, we look only at the foreground wait events. And they have specific classes for the foreground wait events and those that are considered idle. Here, this is a select on $v event name, where we have the name of the wait events, and there are thousands of them, and the classes. So basically, we will see the few important classes which have a color in the enterprise manager graphs. And we will see then, you can see that we need classes because there are thousands of them. So if we want to have a high level look at them, we need classes just to know if it's IO or not, and then we will go on the details. And you can see that there is another class for all the strange wait events that do not happen very often. I will spend more time on the user IO classes because, as I mentioned, a database is working on CPU and doing some IO. So user IO are those dark blue that you see, and that's IO from my session. My session has to read some blocks. And the most important, there are many of them that you will see usually. The most important difference is those that start with DB file and those that start with direct path. When you read a block from a session, usually it goes to the buffer cache, because the idea is that if you need that block, probably another session will need the same soon, and then we keep it in the shared buffer cache. And those reads start with DB file. You may see other IOs that are direct path, and those are those that do not go through the buffer cache. You read them directly to your session. The names are really misleading. DB file, all those ones will read database files. Direct path can read data files. So the names are really misleading, because at first those wait events were instrumented by the developers depending on the place in the code where it is, and direct path is just direct, it bypasses the cache. We will see the details on them. So this is an example that is there just because it's funny. Too many IOs there, and we looked at what happened, and we asked to the user, and finally a user was running a job that it was not needed at all. So finally we dropped the user, and this is the way we solved the problem. DB file. So those ones that start with DB file and ends with read, there are three important ones: DB file sequential read, DB file scattered read, and DB file parallel read. And again, the names are very misleading. When you talk with the storage team, sequential read means you read contiguous blocks. And here, it's completely the opposite. I will show where they happen in the execution plan. The DB file sequential read, you will see that when you access by the row ID to a table block. And usually that comes from the index. You have an index. From the index entry, you go to a block. And then you read the next index entry, and then you go to another block that is probably not at the same place. They call that sequential because of the way it is used. You read one from the index, and then one from the table, and then one from the index, and then one from the table. But they are what we call random reads from the storage point of view. So that's important to know. Better name, in Exadata, they have renamed a few wait events, and they call it single block, and that's the real meaning. The DB file sequential reads one block, 8K in most of the cases. And when you see that, it's probably coming from an access by index. Can be also chain rows, where you follow a pointer to go to the block. The other one, scattered read, that's the opposite. You don't read something that is scattered in the disk. You read contiguous block, and that's one IO reading multiple blocks, multi-block reads. And that's typical of table access full scan on table. You read large amount of blocks because you don't need to go to one or the other. Why is it called scattered? Because they read it sequentially, but they scatter it in the buffer cache. They go to the buffer cache, those that start with DB file. So multi-block reads, single block reads, remember the name. All is documented. If you have a doubt about a wait event, better than guessing from the name, look at the documentation. And another one that is interesting, I mentioned that when you access through an index, you read one and you go to the block. And if the blocks are scattered randomly in the file, then it may be more efficient to read a few index entries and then get a bunch of blocks from there. And that's the DB file parallel read. Why parallel? Just because the system call will ask for many blocks that can be read in parallel with asynchronous IO. and that's what you see in the execution plan with index row ID batched. So it takes, it reads a few index entry and is calling for a batch of blocks to get. Then when you see the wait events, you have an idea about the workload. And if you are seeing a lot of scattered reads for an OLTP application, that's probably a problem, because in OLTP, you read a few rows, then you expect an access by index. If you are seeing sequential read for a big report, that's probably not the best, because you need a lot of rows and you don't want to get those rows from many places. So you match what you see in the wait event with what you expect from the workload that is running. Just going fast on this, because you will have a session on AWR reports. So those wait events, you see them in the AWR reports. And what's interesting with DB file sequential reads is that they read single blocks. They are single block reads. So you know that each read reads 8K. Basically, the metrics that you want to see for wait events, especially I/O, is the number of times you did the I/O. And for sequential read, it's also the number of blocks that you read, and the latency, which is an average. So the latency for I/Os, you need to look at that knowing your disks. For example, 13 milliseconds, that may be okay for mechanical disks. Probably it's too much for SSD, so maybe there is some problem, overload. But be careful, the metrics that you read are weights and the time. And then you can divide also them. You can also divide the number of weights, so the number of I/Os, by the elapsed time. I don't have the elapsed time, but I know that this time is 77%. So I guess the elapsed time. And then if I see that and I do the math, I see that I'm doing 60 I/O per second, which is not a lot. And I do not expect this latency, but be careful when you do those maths. This elapsed time is actually many hours, and do not do any average on something that is large, because probably during those 20 hours, I had a peak of I/O, and those one had a high latency, and then doing nothing. So you can do some maths, but be sure that you are doing the average on something that is homogeneous and not having the peaks. And this is also why active session history, or we will see some tools doing the same, why sampling the wait events on every seconds or 10 seconds can show you the peaks, where the AWR report, especially if you take it on many hours, will not show you this activity. Just looking at the time, and it's going fast on that, but user I/O are the most important ones. The DB file sequential reads is a single block read, and then you can match that with the number of blocks reads, which are the physical reads. If you remember, the number of wait events, 4,000,004.5. I can match that with the number of I/O requests. Of course, it's an I/O call for each one. And I can match that with the number of blocks. Physical reads are actually the number of blocks, and physical reads cache are the number of blocks read to the buffer cache. And DB file sequential read is a read to the buffer cache, because it's not the direct path one. So you can match if you are not sure. Of course, you look at the documentation, but on small examples or on your activity, you can match the different metrics. Those are statistics, and you can match that with some wait events. Okay, and then the idea is not to stay there. If you know that you are spending too much time on I/O on DB file sequential read, then you have matched that with the number of blocks, and then you look at the queries that are reading a lot of blocks. And again, I match it. Physical reads is a number of blocks. I know that I did, that my I/O problem was 4.5 million reads of single blocks, and I see one query here reading most of them, 3.4. So then I will look at this query and look at the number of executions. Maybe it's it's executed too much, or maybe the execution plan is reading too many things. So the entry point here was the wait event. I see a lot of blue, I see a lot of IO, I see that it is DB5 sequential read, then I go to the query, and then I will have to tune the query. The solution doesn't come from the wait IO, but at least you know where to look at. DB file, something that goes to the buffer cache. This is a diagram that is taken from a presentation about Exadata, but just to show the idea, when you read to the buffer cache, those are the DB file something, but if you have large full scans to do, I mean, when you read a few blocks, you put them in the buffer cache because probably other session will need them. It may be a small lookup table, it may be index branches or things like that. If you full scan a table, you do not expect that everybody is scanning the same table all the time. So you do not take the override to put that in the cache, you just read it in your session, and this is what means the direct path wait events. Direct path means just that you go from the, you read from the session without putting it in the buffer cache. And there are two main direct path reads. One that reads the data files, and one that reads the TAM files. Reading the data files, that's the case I mentioned just before, full scan of big table, you do not want to go through the buffer cache for that. You read directly with larger IO size from the disk. So usually full table scan or index fast full scan, multi-block reads. If you see a direct path read temp, that's from TAM file. When you have to sort or hash something and it doesn't fit in memory, then it has to be spilled to disk. And those are the direct path read or writes. I have an example there, but I will open the SQL mon it is coming from. I've just added that this morning because that's something I have seen at a customer a few days ago. So this is a SQL monitor for a query that was long, and actually we had a problem on the system and we reproduced it with the query. Something very simple, a full scan and an order by on it. And where do you see the wait events with a SQL monitor? So SQL monitor is really cool, but you need diagnostic enterprise edition, diagnostic pack, tuning pack. So it's expensive, but cool. The activity, the wait event activity, you see it in the activity tab. And this is a wait event in the user IO wait class, direct path write. You write to the TAM file because it doesn't fit in memory for a sort, for the sort that we have seen here. We have seen activity in the sort operation, and you see under my mouse there, direct path write temp. Most of the time was spent there. I had some reads here, most of them in CPU for the full scan, probably because that was in cache at OS level, and waiting there. And something quite usual. So here it's the time it
Franck,
has taken. Yeah.
Just one question I think would be nice to answer now.
Yeah.
Małgorzata asks, is there a way to check statistics on short queries that are not present in ASH, in active session history? So I think that the same would be, for example, if there is a possibility to check those things without diagnostic pack, right?
Yeah, so we will see what we can do with TKProf. But most of the time, if you have diagnostic pack, short queries, you don't care if they run just a few times. Short queries, you care if they're executed a lot, and then you will see them also in the samples. So it's not about short queries or long queries. one occurrence of a long query, you will see it, but a lot of occurrence of short queries, you will see them. But we will also look at TK-prof, which really shows you every wait events, even if it's very short. And there, the query was long, and I was mentioning the read. We do not see them, the full scan read, because it was quick, probably from cache. My problem here was that the I/O was really long, and I've seen a wait event for this direct path write that took 1 minute. We had a problem on storage level, actually on ZFS level. And you can match that there with some activity in the memory. Here, you see that the PGA usage has increased while reading the table. And then we reached the 800 maximum that I had in my session. And then Oracle wanted to put this in the temp files. And I can see that the write happens only 1 minute later. And that I match that with the wait events to understand what happened. So this is where wait events are useful. I match some statistics with the wait events because nothing happened there. We were not in CPU. And I want to understand what happened there. And this is where matching those, I have seen that I was already in the wait event during that time. And that was the idea for the wait events from the beginning. You have something, you don't know what happens because you have no statistic telling you what happens there, but the wait event tells you what happens. I'm waiting for the system, and 1 minute for an I/O is quite long. Okay, so for the I/Os, the interesting thing is that the average wait time, you should have an idea about your storage. For example, from mechanical disks, you expect a few milliseconds.
Frank, sorry to interrupt you once again. Mogulata says, yes, but you are preparing a POC based on a short query that might be executed a couple million of times in the future. If statistics are fine, just couple executions. So I think then
I go to TK-prof there, because there I cannot rely on sampling every second. So I have a short query and I want to see all wait events for them, and that's TK-prof, and we will see.
And you are independent from the licenses, right?
Yeah, TK-prof, you can run that even in standard edition without any problem. But TK-prof has an overhead. So that's perfect for a lab where you want to reproduce a problem, And so if you have mechanical disk, you can expect a few milliseconds from there. If you have SSD, you expect less. So you can match what you see from the wait event with what you expect from the storage. And that's also the value of it. Looking at the wait event, especially the average wait time for I/O, you know that you have to go to the development team to tell them there is something wrong, you are reading too much data, or go to the storage team telling them your storage is too slow. So you can match that with the specification of the storage, for example. Okay, I think, still on user I/Os, but just to mention that in general, in addition to the name of the wait event, there are a few parameters. And for example, when you have a DB file sequential read, so remember that's a single block I/O, you have parameters that tells you the file number, the block number, and the number of blocks. So number of blocks for sequential read, you expect 1 because it's a single block. But from the file number and the block number, you can look at DBA extents and then know which data file it is and which segment it is. For example, you can know if it's from an index, if it's from an undo segment or anything. We will see. I will go faster maybe on the next slide because I want to show you some things live. But when you have a problem with I/O, what you want to improve, If the average time is too high, then look at the storage, go to faster disks, or maybe you have fast disk, but it's overloaded and then you are queuing for it. And if the count is too high for what you can expect, for example, if you are reading thousands of blocks just to get one row, then probably you have a problem with the execution plan. Maybe you are missing some indexes. So few ideas, and that's quite general. If when you want to improve something, do less work. If you reduce the logical IOs, then probably you will also reduce the physical IOs. Maybe increase the buffer cache if you think that you are reading a lot just because it doesn't fit in the cache for the frequently accessed data. Maybe look at the PGA if it's IO related to spilling to temp files. Or do it faster, reduce the disk contention because there are queues in file system, there are queues in disks, there are queues everywhere. Maybe add more disks so that they can work together, and then you increase the IOPS. So that's the bad thing. And also just to mention that you can match that with some statistics in Enterprise Manager. You have also, and also in AWR report, you have also some statistics about IO requests by function. So you can match, I have a lot of blue there, and that's IO, and then look more precisely to IOs to know if it's Orman or something running there. Okay, and now it's your turn to work. So of course, nothing mandatory, but if you want to look live at some IO, I have opened my, my database. I will paste the information in the chat probably. You can, if you have a browser, you can go to this URL, which is the Performance Hub, the Enterprise Manager Express, and the user is C##POUG. If you know multi-tenant, you understand why C##. And the password is POUG Workshop 2020 with spaces there. I copy paste that in the chat if I find it. And I show you all panelists and attendees. Okay, here in the chat, you have this. So do not try to do nasty things with this user because I don't really remember what I've granted to it. The idea is just to look at this. So if you go to the URL I mentioned, and you have, it asks for a username, C##POUG, for a password, POUG Workshop 2020, it's case sensitive. You put nothing in the container name, you log in. You probably have to accept some certificate things because it's HTTPS, and you should arrive to something like the main page. That's not the main page. Oh yeah, shell. Yeah, okay. And in the meantime, so just tell me if you have a problem, but you should not have any problem with that. I will run some activity in the database. I will explain after what I will run, but the idea is that you can also look in this Performance Hub and see what I'm running there. So this is currently running. I see some activity. What I wanted to mention. Yeah. So when you go to the URL and when you have a successful login, you have the main page, which may be long if we are all connected, but let's try that. And from the main page, if you go to Performance Hub, you have this page where you can see the number of active sessions. And you can refresh every 15 seconds if you want or not. And if you got all that, you can see the activity that I've just run. and you can see some user IO there, the blue ones. And from there, those are the weight classes. And I can see more details there, detail about the queries, and also I will put the detail about the weight events. I can also put the weight events here if I want, and I see all the weight events, but a good idea is to look at the weight class from the high level and then check the detail. And I can see that I have here some, sorry, I selected the CPU only. I wanted to select, going back, weight classes. Here I click on the blue one, so the user IO, and then I see only the user IO. It's filtered on weight class user IO. And then I can see the weight events that are behind those user IOs. And most of them are direct path read. If you remember, direct path read is probably a full table scan. I can also see some information here about the SQL plan operation. And I can see a table access full. I can see the SQL ID, and I see 2 SQL IDs, and this one, I will go to it, and that goes to the SQL monitor, but basically you will see the full scan that I'm running, a select count from a table. Okay, I'm just looking if there are any questions there. No. If there is something in the chat, load very slow. I guess 50 people log in at the same time, yeah? Yeah. So maybe do not refresh every 15 seconds. That's a good point. I don't have a lot of CPU there. CPU. That's on the Oracle Cloud with my Oracle Ace Cloud credit, and I have only provisioned 2 CPUs, so yeah, it takes a lot of time. And in addition to that, I run some activity, and I will run more activity, and you will see the colors. So you can look at that while I'm talking on the other slides, if you want to see a bit more what I've run there. And I will show you something else. So you know the IP where my database is, you know the user, C## POUG, and you know the password. I've opened this port, which is the Enterprise Manager Express port, but I have also opened the listener port. So if you have any other tool to look at the performance, you can do it. I expect that the load will not be too much for these databases, but for example, but I will mention it afterwards, if you don't have diagnostic pack, because this requires diagnostic pack, if you don't have, I use sometimes the hash viewer. I will show you where to get it, but you can also Google it. And this shows you a similar view, sorry, not that one, a similar view on it, where I can see also my select statement and anything. And this doesn't require a diagnostic pack because this reads $V session. Okay, I let that open with just some activity running there, and I will go back to Performance Hub. So here you select the time range, and yeah, right, it takes some time to display. So please do not put auto refresh, and once it is refreshed, then you can look at them. This tool is really interesting because you can see the detail, you can choose many dimensions, the user, so you can really drill down. From what you see at top level, the weight class, you can really drill down and find the user, find the statement, the plan. You have this view with the time, but you have also a view with a map like this. For example, I see the weight event classes, and for each one, the weight events, so you can play with it. Okay, that is running. I will continue on the slide. I will look at the time, and for sure I will show you TK-Prof and things like that later. You will have the slides, and I have put also some notes in the presenter notes that I will provide you with the PDF, so you will have other information. So next weight class that you will look at, I mentioned that user IO, you expect them. The others, you should not expect them, or at least you need to look at them. The application weight class is about the application locks, the unqueues that are related with the application. And what means related with the application? The locks that either you set yourself because you do a select for update, or you do some DML that has to wait on rows, or on or you do some DDL that has to wait for the end of transaction on the table. So that's an example where a table was locked and then sessions accumulated waiting for it, and you can see how it grows. And when it's red, that means that the session is waiting. So you have users waiting without any answer from the database. So of course, that's usually bad. When you look at the detail, so that's the wait class. When you look at the detail, you see the wait event, and then you look at the definition, unQTX. TX means transaction, and when you wait for a transaction, it's because you have seen that a row was locked, and then you wait for the end of this transaction. So when you see that, look also at the blocking session, at the tree of blocking sessions, to know which session is blocking everybody there. And then decide, maybe you will kill the blocking ones, or you will contact him and see what he is doing. So when a row is locked, you will see unQTX wait event. And that's basically select for update or update of modification on a row, and it waits on it. It can also be a lack of ITLs, and you will see the detail in the P1, P2 things, but I will not go into that detail. What you do when you do that, so immediately identify where it comes from. Maybe a user is blocking something, and also look at the application logic. Normally, an application should not leave a transaction open outside of user transactions, but there are still some applications where if the user just go home with the screen of the application open in the middle of a transaction, then the transaction on the database is also there, and everybody is waiting on it. So look at the application logic if you see frequent things like that. Reduce the transaction duration. So if something is slow, a side effect can be higher locks, just because a short lock is expected, but if something else is slow, then you wait for it. And that you also see if you see other wait events than this one in the waits. That's unQTX, the wait on transactions. So DML, contention on rows. If you see unQTM, that's different. That's a lock on the whole table. And that is not expected with DML. This unqueue, this wait event, is there to be sure that when you do some DDL, like rebuild an index, which is not a rebuild online, that you wait that all modifications are committed on it. So usually you don't see them because you do not do DDL while the application is running. One case where you can see it is because of the non-indexed foreign keys. If you delete a row from a parent table and then it has to check that there are no child rows in the child table, and in this case it may lock the whole table, and the solution is to index the foreign key, but I will not go further on that. Do not delete or update the key on lookup tables, or index the foreign key Those are the solution, and no DDL in production except online operations. Okay, going fast on those. The commits, I mentioned that log file sync is when you wait at commit, and you see that in orange. I'm going fast on where you can see that, the log file sync. Basically, you need to look at too many commits or too many redo generated by long applications. When you do a commit, you wait for the log writer, and behind that, there is probably an IO also. Look at the average time, look at the count, and that's probably to be matched with the commit count. And there are some applications, some batch that are committing for each row, and that's bad because each commit has to wait. And then look also at the application logic for that. If the average time is too high, then look at the log writer, look at where your redo logs are, maybe put them on faster disks. If it's the count that is too high and not the average, then look at the application doing row by row commits, basically. So do less work, less commit, less redo generated with no logging application. If you're in data guard, you do not only wait for the redo logs, you also wait for shipping to the data guard and applying if you are in SIP. So look also at the network latency that is behind, and faster disks. Okay, I go fast because I've put a lot on slides just as a reference. System IO, the difference between user IO and system IO, system are the background processes. I just show you an example I had recently. So DB writer was busy, and we see that with system IO and some wait events coming from DB writer. How did we solve that? We didn't solve that immediately, but the first thing was adding a log device in ZFS file system again. So here, you clearly identify that the latency is too high, and then you go to the storage to look at some reasons for that. So system IO, it can be backups running, that's system IO. It can be contention on control file writes. You will see the wait event control file parallel writes because you multiplex the control file. So this is why it's parallel. And then look at maybe too many log switches, too much redo generated, redo logs, online redo log too small, and then too many checkpoints. And log file parallel write, that's what is behind in the background of the log file sync, and then look at the writing to the redo. So if you want to do that faster, low latency disks, especially for redo control files, and yeah, and that's for them. About configuration, so those are the brown ones, which are ugly for a reason. You should not see them on an instance that is correctly tuned. The red was more application. You have something to do on the application. Those ones are really about your DBA job. For example, if your recovery area is full, you will see a wait event there telling you that everybody is waiting for that. So recovery area full, archiving needed, log file switch, that's the wait event. It can be also checkpoint incomplete when redo, an online redo has to be overwritten, and you wait for the end of the checkpoint. So configuration, you look at the wait event, its definition, and look at the configuration of your database, of your instance to solve that. You should not have those one, and monitor them. Huh? If it's brown there, you have something to do immediately. Huh? Okay. If it's about log file switch, then you will try to generate less redo. Look at the application. Maybe it writes to permanent persistent table and you need global temporary table. Maybe you need some no logging operation. Look at $, recovery area usage, all those things. Concurrency ones are read as well, but it's not the contention on data, on rows, it's more contention on memory. And it can be because of parsing. If you don't use bind variables and you parse too much, I mentioned that you use a lot of CPU, but you also access a lot to the shared pool, and then you may wait for it. So the wait events that are behind concurrency, some concern the buffer cache, buffer busy waits. We'll show an example later, and library cache, that's about parsing. Again, I'm going fast on them. Buffer busy wait, find the odd blocks. Maybe the last block of an index is always used because you insert with increasing values. Full table scan or OLTP session may compete reading always the same blocks. And yeah, that's about buffer cache, buffer busy waits, and library cache lock. That's about parsing. The time is going very fast, so I will let the idle ones you will see SQLnet. You are waiting for an application and just look at it, and maybe you have too many sessions in the connection pool. You can match the time waited with the connection pool. I'm going fast on there. I will not mention the cluster ones. That's if you run in rack, there may be some contention between nodes and you have wait events for them, and they are in this gray for cluster. And other waits, those are all the waits that are not classified elsewhere. And I will just show an example. So there are a lot of them. Each case is specific. I will just show an example where I had Herman that was blocked on NFS. And the call to NFS was blocked, and that blocked Herman. And that was the wait event disk file operation, because Herman had to write something, and then to the control file, and then control file contention, and that was the others there. And the consequence of control file contention is that the log file sync was blocked as well, and then all sessions wanting to commit was there. So by looking at the wait events, it helps you to understand what happened, for example, in the past. For those, look at them, the definition, try to reproduce and understand what happened. And now we have just 15 minutes to see the tools. Here is a link to the documentation. The wait events are documented. Do not guess on their name, just look at them in the documentation. And the tools, you have some tools that will show all the wait events, like TKProf, I will show you. You have some tools that will show cumulative statistics, like the $, session event. And if you have diagnostic pack, or if you have a tool that samples on a $, session, that's sampling, and it gives a good idea, but not all wait events. And for SQL trace, I will show you on my demo screen there. So TKProf, you can run that everywhere. So this is the most interesting one. Let me just push that. Yeah, we see everything. I am connected. I check the PDBs. I will connect to the POUG PDB. And on purpose, I'm setting a small SGA and a large shared pool to have a small buffer cache, because I want to reproduce a problem. Those are the default statistics, so nothing to change. SQL trace will generate a trace file. You can put an identifier to find it easier. This is how you set SQL trace. I reference Tmall website, so I will not go to the syntax there. I'm just running a query there where I'm forcing an access by index. And this writes to the trace file. So it has an overhead, but that's also something we use sometimes in production if we really want to profile everything and see what is running. While it is running, and because we will be short on, yeah, okay, it's fine. If I look at the execution plan, I can see that's what I wanted, an index range scan. I disable the trace, and I will run tkprof on it. I get the name of my trace file from diaginfo, the default trace file. And this is the header of the trace file. I do a cat on it, so that's the raw trace file where you see all wait events. Here, a lot of DB file sequential read. You may want to go to all details, but first you will run tkprof on it and check the statistics from tkprof, like there, where I can see my query. As I mentioned, I see the elapsed time, so 27 seconds, 14 in CPU, so the remaining in wait events, in non-idle wait events. The SQL nets are the idle ones. I waited 3 seconds before running my statement, but the interesting one is DB file sequential read here. So I know that when I was not in CPU, I did 23,000 single block IO calls. And on average, you can divide, it was not a lot, but that was for a total of 14 seconds. And then you look at the execution plan. Is it really what you want? So I get back there. So you see that I've done an index range scan. I have read 23,000 blocks from disks, and that's single block reads. So maybe it was not good to use an index range scan for reading all those many blocks. And I return only one row. So there's probably something to do if I don't want to read all that for only one row. While we are there, I show you quickly the $V views that I mentioned. So the session event will show the cumulative wait events for my session in my session. So that's my session, that's session event. I see the time waited and the number of times I waited. So the DB file sequential read, the 23,000 of time, and the total time. Difference is that in this view, I have only those big numbers. In the trace, I have each one. I have 23,000 of lines telling me that I have sequential read. I just call DBMS session sleep, which sleeps and then waits for something. And we can see it there. I slept for 3 seconds. That's the wait event that is behind and one occurrence of it. You have also wait event history, which shows the 10 last wait events, just showing that. Here I had a few round trips between my client and the server, so that's SQLnet message from it. Session wait history, and if you have diagnostic pack, you have the active session history, which sample the $V session. And then you see not all wait events, not the 23,000 of them, but some samples and with more information. And the information for DB file sequential read, I know the file, the block, and then I can query from DBA data file. I know the file, and from DBA extent, I didn't put the right number there, but from DBA extend, if I put the file number, sorry, block. So file number was 1, so that's probably system. And the block number here, I know that this sample was doing a read for the block belonging to this extent. Demo index. Yeah, I've created it in system, which is not a good idea. Okay, what time is it? Yeah, we will go fast. Just to show you that those wait events are calls to the system. And then you can see them with strace if you are on Linux. I'm just showing that if I run the wait and I strace, I'm going fast on that, but just to show you that there is a call in behind. The call that was behind my session sleep was this one, 5 seconds. So from the system, I can see it, but this name is not easy to match. The wait events are documented by Oracle. And you can also, from the command line, you can use tunnel podder snapper if you want. So I run some activity there. And if I run snapper, you don't need diagnostic pack for that. It will sample the VDollar session and give you an idea that I have, on average, 1 active session in TM contention. So this is with text, the same thing as 1 session in red in the graphs. Okay, 7 minutes. So just to mention that you have also a view, and in the IWR report where you have some histograms about the wait events. So not only the total average, but the average for some ranges of time. And that's interesting for IOs. For example, here, I have an histogram for my single block IO reads. And there I can see from the time it takes that if I am in few milliseconds, that can be mechanical drive. If I am in 100 of microseconds, that may be SSD behind fiber channel. So if you know what you have behind in your storage and you compare that, you may know how many reads were from the disks or maybe from cache in the storage, because in microseconds, then that cannot be disk, and that's probably memory. So you can investigate, and that gives you some information when you go to the storage team to tell them that their storage is low. We have seen Snapper. I just show you, and you have all links, and it's really easy to connect. Hash Viewer, that's something you can use to get a graphical view without diagnostic pack. And to connect, you can connect to my database if you want. You have all information. You have the IP address, you have the port, and you just need the OGDBC jar, which I take from the SQL developer. So there are many tools with graphical view, even if you don't have a diagnostic pack. I think we don't have the time to do that now, but you have all information if you want to look at Hash Viewer. I will not open my port on the database for a long time after the presentation, but you can try that on your database as well. And what's left, just in 2 minutes, when I said DB time is CPU time plus wait time, that's wrong, because there is some time that is not accounted as wait time and not accounted as CPU time, and this is when you wait for the CPU. What I want to tell you there is just that if you are in CPU starvation, then do not look at the wait events. And the reason is that the instrumentation of the wait events, if you remember the call, the instrumentation is done around with instructions that are in CPU. And then if after the IO, you wait to be able to run in CPU, then this time will inflate the wait event. So first, if you are in CPU starvation, do not look at the wait event, solve the CPU problem, and then when you know that you do not wait in the CPU run queue, you can look at the wait events. Solve the CPU problem on the server first before looking at the wait events, or they will be inflated just because of the time spent in the run queue after the system call. And be careful with hyper trading. You cannot run at 100% when you are in hyper trading. So you may be in CPU starvation even if you are not in 100% CPU usage. You can use instance caging, and that even in standard edition, so that before the OS tries to schedule out your process, the database will do it, and the database does it better because it will not schedule out a process that holds some latches, for example, and you reduce the contention if you do that at database level. Okay, I went very fast because we all think that 1 hour 30 is long, but it is actually very short for this kind of topic. The most important, do not rely on the names. Look at the documentation or official documentation or blogs from Jonathan Levis, for Tunnel Powder. You have a lot of information on wait events. Basically, there are two ways to improve the performance. You do it faster, or you do it less times, or you don't do it at all. And with wait events, you have the two, because you have the wait time and you have the number of waits. So this is where it helps, and it matches what the user feels. If I have a user telling me that the database is too slow, but I see that the activity on the database is very low, probably the problem is elsewhere. If I'm waiting only on a SQLnet message from client, then that's not a problem in the database. On the opposite, if I see that I'm waiting a lot on I/O, but I'm not doing so many I/Os, but I just wait too much on that, then I will look at the system, at the storage level. So look at the wait time and try to reduce the latency. And this is a big summary about the wait events. So I've put some cocktails, but that's about the colors. Green is okay. Of course, you may need to reduce it if you are doing too much thing, but green is okay for software, that's CPU. User I/O, that's okay, but in OLTP, remember that you try to have everything in buffer cache and then access to RAM, and that's green, rather than to disk, which is blue. If it's red, look at it. Some things are blocked. Maybe the application is doing bad things with the logs. Commit, look at your redo logs. Those ones do not scale. If you have already a bit of orange and a bit of red, when you will have more users, it will be a problem. Even if they do not fill everything long for the moment, then they will have a user. The other ones, look at the documentation, try to reproduce small use case, TK-Prof, look at that. Okay, I'm sorry I went really fast, but you will have time to look at the slides later. Is there a question, and do we have time for questions?
Frank, we have actually two questions right now. The first one, I think will be faster. Will be faster to answer. If system I/O is the background process and DB time is only foreground, why the tool puts both together? So I think there was a bit of misunderstanding here.
Okay, so the tools, those tools will not add them. They will not show them. And those tools, where is it? This one, you have the choice if you want to see them or not. If I get back to the view like there, you can check the background activity. I don't know why I cannot check it, but this should be something that you check or not. So you can decide to see them or not. Usually you do not look at them. For example, you look at log file sync, but then if you have a log file sync, you want to see if it's behind a wait event waiting to the redo logs or waiting for data guard, for example.
Okay. And the other one is, well, a bit more complicated, I think. How we can measure and identify a CPU problem, for example, to be collection in PL/SQL, or I think a collection that is misindexed. How can we identify that?
I think that one you can keep it for Tune just after, and as he will show you some AWR report, I think he will show you some time model, and then from the time model you will see more the user part of it, which is running in PL/SQL, running in SQL, or something like that. The wait events are more focused to the system, the layer under the database, and the time model is more about the different kind of calls.
Yeah, but so, the time model is not going to pin me to this session, right? It's more like in AWR per snap telling us that this is, here we have very big PL/SQL execution, but later on we have to pinpoint the PL/SQL itself.
For CPU, then you look at the statistics. Wait events were made for that part that is not in CPU, and because it's not in CPU, there are no statistics, no counters, because it's not in CPU. So wait events are there to put some numbers, some metrics for when you are not in CPU. When you are in CPU, then you have a lot of statistics, and again, they have names that can be misleading, but they are documented and all that. So for example, you have statistics with the pass time, with execution time. And
so the basic answer is start with the time model and drill down to statistics per session.
Yeah. If I see some time in CPU, I will look at the logical reads, because most of the time is spent in logical reads in OLTP application. But of course, it can be something else and parsing, and then that's another problem.
Yeah. Okay. Yeah, okay. And Mariusz asked why there is no beer on a cheat sheet.
Yeah, I put some cocktails. Do you know blue beers and red beers? I know pink beers, I'm not sure, but for the colors, I know a lot of beers, but not blue beers. But it probably exists.
I'm not good with colors. Everything can be blue for me. So
yeah, so that's perfect. You can take beers.
Thank you, Frank, very much for awesome session.
Thank you very much for organizing that.
Frank,